I'm at the bottom of the second page of your notes handout. So a big idea, if we're investigating limits as x approaches positive or negative infinity, we're looking for the terms that dominate our function. We can, like we did with that, the little +1 on that function we saw, the square root of x over the square root of x squared plus 1. The +1, it does whatever the opposite of dominating is. It becomes insignificant, and the x squared term inside the radical begins to dominate. So that's what we're going to do to investigate these limits. So that's what goes on your blank there. Identify the term or terms that dominate. So you're going to write in these two examples. So start as example 7a in your textbook, but I've modified it. So I want to find the limit as x approaches infinity of this giant rational function. So the way I'm going to do that, I'm going to imagine letting x get larger and larger. I want x to approach infinity. And think about that numerator, 2x to the fifth plus x to the fourth minus x squared plus 1. If x is a giant, giant, giant number, then that little +1, it's hardly going to change the value of that numerator at all. And in fact, we can think that all through and decide that in the numerator, the term that's going to affect the value of the numerator the most is that first term, because it's got that biggest exponent. It's going to grow the fastest. The term that dominates in the denominator, 3x squared. So if you ever talked about end behavior in your pre-calculus class, it's the same kind of idea. So imagine a new function. I still want x to go to infinity, but now I'm considering this new sort of streamlined function, 2x to the fifth over 3x squared. And I can imagine simplifying that algebraically. I can cancel an x squared from the numerator and denominator, simplify that rational expression, and get 2x cubed over 3. Well, now that I've simplified that down as far as I can understand the behavior of the function. Now I can imagine letting x get bigger and bigger and bigger. What happens? The numerator is going to grow and the denominator is going to stay at 3. So a really giant number divided by 3 is going to be still a really giant number, and here the limit we would say is infinity. Of course, infinity is not a number that is finite, so you could also say here that the limit does not exist. If your limit is ever infinity, it would also be appropriate to say the limit does not exist. So if our goal was to say whether this function had a horizontal asymptote, I found the limit of the function as x approached positive infinity, and I did not get a number. I got infinity. I did not get a number. If I had gotten a number, then y equals that number would be the horizontal asymptote. But here I didn't get a number, so this function has no horizontal asymptote, at least not as x approaches positive infinity. So try this one. The limit as x approaches infinity of this different rational function. We're going to go through that same process. Imagine thinking about the term that dominates in the numerator, the term that dominates in the denominator, and my function is going to behave, even though it's this really complicated function, it's going to behave like this function as x gets closer and closer to infinity. Notice my x cubes can cancel. I can simplify that expression. So my new expression, the limit as x approaches infinity of 2/5, it's the limit of a constant, which is that same constant value. So here, since I did get a one number answer as I let x go toward infinity, this function would have a horizontal asymptote at y equals 2/5. So you're going to go to the top of page 3 now and practice finding those limits. Again, you're looking for a term that dominates in the numerator and the denominator. You can perform whatever algebra you can. Do not take off your limit expression prematurely. So notice here, it was the limit as x approached infinity of, I had the big fraction first, and then I looked for the two terms that dominate, the one in the numerator and the denominator. I'm still taking the limit. I haven't finished taking the limit, so I need that expression there still. That function, that operator, a limit as an operator. And it's not until I can actually either substitute x in, or I can tell here that I have a limit of a constant, that I can say I have a one number answer. And do not fail to notice that I've asked at the end of each question that you decide if there's a horizontal asymptote, and if so, where. All right, so we talked a little bit about what mathematically happens to make a horizontal asymptote. For a horizontal asymptote to exist, there must be a limit as x approaches infinity or as x approaches negative infinity. So it makes a vertical asymptote happen. Let's go back to our function y equals 1 over x, and this function has also, it has a horizontal asymptote that we talked about, it has a vertical asymptote too. That's at the place where x equals 0. So you could imagine letting x get closer and closer to 0. If I replace these x values with numbers that are less than 1 and getting closer and closer to 0, my denominator becomes extremely small, extremely close to 0, which makes my whole expression grow closer and closer toward infinity. Or, since this is a fraction and I have a positive number in the numerator, if my x is negative, if my denominator is negative, I'm going to have a very big negative number as x approaches 0 from the left. So you can see that I said that here. So let's talk about an actual definition for a vertical asymptote. A function has a vertical asymptote if the limit as your x approaches some value, here we happen to have called it a, some value from the right, and the result is either positive or negative infinity. Or if you approach some number from the left and the result is positive or negative infinity, then we say that a function has a vertical asymptote at that x value. And again, I just put a note on your paper, so make sure you write this in to the box at the top of page 4, and note that if your limit is infinity, infinity is not a number, so a limit of infinity isn't a limit, so at that kind of place, the limit fails to exist, or you could say does not exist. I was just about to walk through this example when I found a giant error in my PowerPoint. So I'm afraid that I'm not going to be able to fix it and get this posted in time. So here's what we're going to do. Feel free to read through this. We're going to do this example tomorrow in class. So your goal now is going to be to try the rest of this paper. This practice, now it's supposed to be very challenging, so don't let it get you too frustrated. The idea would be to make one graph that has all of these things true. If that's too frustrating, then I want you to pick 1 or 2 of them at a time. Make me one graph that has 1 or 2 of these. So see if you can make a picture for all of them. Ideally, you're going to combine that into one graph, but do what you can. So, and then would you please give your best effort at this assignment. There's going to be 1 or 2 in there where I ask you to evaluate the behavior of a function to the left and right of a vertical asymptote, but we just said I'm not going to have a video on that. We'll do that one in tomorrow. So if there's homework problems like that here, you can miss those. And we're going to talk about analyzing a function to the left and right of a vertical asymptote in class tomorrow. But give your best effort on the rest of this handout, please. Thank you.